Okay, so far in this section, we've talked a lot about reducing power. We kind of talked about voltage domains and how that the voltage is quadratically related to power and frequency is directly related to power. So we have these voltage domains where we try to figure out the minimum amount of voltage that we need and the minimum amount of frequency we need using dynamic voltage scaling in order to be able to obtain the bare minimum amount of power that we need to actually operate the circuit properly. In this case, I kind of added a combining concepts portion here. So this is kind of an outside the box type thinking here. So this is a good way to kind of combine concepts into an exam type question, since I know those are what you guys care about. So we have this concept of instruction level parallelism. So before, if you recall from 385, you have a number of stages in a data path, right? And then ultimately what they're trying to do is we're trying to have parallelism. And so in this case down here, I've defined it as replicating a single functional unit n times. And you're trying to get it to increase the throughput. So you've increased the area of your device, but because you're using more of it and you're getting efficiency, you might be able. Okay, so let me ask you this question: if you have multiple devices running multiple instructions and you're increasing your throughput, what could you potentially do to reduce power? Since you've got increased throughput through multiple parallel data paths.
Increase the voltage.
Well, decreasing the voltage is just general. But I'm saying specifically, we significantly increased the throughput by adding more area. So we've almost doubled our throughput because we're doing twice as many instructions now. So let's say you're looking for a design compromise. But by doing this, you're increasing power. So what ties into power? Well, what's your power equation? Dynamic power equation. No? Dynamic power equation. As I say, I've only said this equation about 100 times in class. There you go. Times. That's energy. You said everything except what I'm looking for. I'm trying to lead you to the answer. Yeah. Equals 1. So energy is equal to 1/2 CL/VDD squared. So what's the relationship between energy and power? What do I have to multiply both sides in order to get? Frequency, there we go. So I got frequency and now we're at power, right? So if I have this cell and I have two parallel data paths and they're executing in a theoretical situation where we're having optimal execution. So we've increased our throughput by 2, right? But of course, we're increasing our power consumption. So they come back and say, we need to reduce our power consumption a little bit. What can you do? There we go. You can decrease the frequency because we've increased the throughput so much that I can actually decrease the frequency by some smaller function. So let's say I decrease the frequency by, it's 4/5, right? So I then reduce the frequency by a factor by 20%, right? But because we've already multiplied this by 2, it's just 2 times 4 over 5. So it just ends up being 8/5, which is still significantly better than this 20%, right? So we use parallelism. We can actually improve the throughput, and that allows us to have to be able to reduce the frequency a little bit. So this is a good opportunity for good design compromise. Does that make sense? Okay. So here we've kind of gone over this. Remember, activity factors for memory are relatively minuscule because the arithmetic logic unit's going to be used almost every single cycle, whereas our memory, we don't want to be using that unless we're doing some sort of load and store operation. So that's another reason why we want to reduce the loads and stores in a data path. And then here I kind of quickly go over parallelism. Here, what they've demonstrated in B, right? Here, this F, this signal, is our frequency. Here, they've actually cut it in half, as we can split it up in order to gain quadratic savings in energy at the expense of doubling the area. So that's what we just figured out, right? What you guys figured out just now is that. And so replacing a single functional unit with an n-stage pipeline unit also reduces the amount of logic in a clock cycle at the expense of more registers. So here, let's say our designer has said, this is too much area. Sorry, we need it smaller. But we need it to run a little faster. So what we're going to be doing is we're becoming this concept of scaling where we add registers in between each stage. So what ends up happening is sometimes, if area is not an issue, these concepts can be combined together of scaling and pipelining. Sometimes this is known as super pipelining. Right? You get the idea. So all of that is done to regulate the energy in between each register. So before we go to interconnects, you see the idea here. You've got these interconnects that tie all of these logic blocks together. So you have to start worrying about that a lot. And we're going to be finding out why. So one of the challenges is what happens when I have a wire going this way and I have another signal going this way. If you remember magnetism, right? If you pass electrical current, first of all, if I have two electrical signals with a distance between them, what is this called? If I have a small distance between two, there we go, capacitance. So if you put your wires too close, you start getting capacitances. And so interconnects is only that. Interconnects are the wires linking transistors together. So if you recall this concept of the tyranny of numbers. Sounds familiar. I've said it a few times. Do you all remember who came up with that? Jack Kilby, very good. And what else did Jack Kilby invent? Very good. And what else did he invent? What did he invent that got him the Nobel Prize? Integrated circuit. Very good. So what I'm referring to, George is like, I got this. So in early days of VLSI, transistors were relatively slow. So you had these slow transistors. You have this huge scale. You have to have very high voltage in order to reach your inversion region. So that's why if you look at old computers and they're running in megahertz as opposed to your typical laptop, which is running in gigahertz. Think about your computer is probably running, 10,000 times faster than the computer that got the Apollo 11 to the moon. And yet it works for a year and a half and then breaks down and your screen goes to crap. And it's like that. Remember that quote earlier in the semester about if we were like, if the car industry was like the computer industry, it would get 10,000 miles to the gallon and explode once a year. So you had these really thick wires, and they had low resistance. However, transistors are switching much faster, so a lot of the power consumption occurs in the wires, and that's because we're going to have to deal with RC delays. Like, oh no, not those again. So often these wires are packed closely together, and there's just a large fraction of their capacitance is to the neighbors. So specifically, this phenomenon that I was just talking to you about is called crosstalk. It's the impact of a switching wire on a neighboring wire through capacitive coupling. So what happens is, let's say my wires are like this. So I have a 1 here and I have a 1 there. So what happens when I change the voltage? What's created here? Well, that's the distance. So, but if I have a 0 here and a 1 here, what is that? Yeah, I've created a voltage potential across a capacitor, which means it's going to be very good at holding the signal, right? But that's not something we want wires doing. That's the exact opposite. We want wires to take a signal and get it over here as fast as humanly possible, or as scientifically possible, because those aren't little humans running inside the computer. So in order to do that, we have to consider the geometry of the wire. I should note I've posted the rough drafts of the of the 3 labs I'm going to have you guys do. They're all going to be due in April. And what you'll see in the first lab is geometry having a lot to do with how things work. So you've kind of already seen that in terms of lambda designs, but you have to worry about the width, the space between 2 wires. So here we have to worry about the capacitance. Then we have, in order to calculate all the resistances, we got to worry about the width, and then ultimately have to worry about the length of the wire. You have the thickness of the wire, and then the height off of the dielectric. So we have to be worried about all of these things. And then what's going to happen is, what happens when I have a 1 here, or 0 here, or suddenly they're going the same direction and then I create the opposite direction? Huh? Yeah. Oh yeah. All that stuff's involved there. So I'm going to...
Is that like the distance from the dielectric? So it's like kind of floating off that?
No. It's the thickness of the dielectric. Right, it's not the best diagram. It should be, probably should look more like this. And that H should be there. Does that make more sense? Yeah. So this here is what's known as pitch. And then the aspect ratio is this is your width here. So how thick is the wire compared to how far is it away from another wire? And so what we're going to see down here in a second is layer stacks. So one of the solutions, we were talking about metal 1, metal 2, metal 3 before. So what you're going to see in this diagram right down here is that they have a certain distance from each other, and this will answer Bo's question in more detail. So you have this dielectric in between all these different wires, so they actually run across each other in different levels. And so what's going to happen is you're going to see metal 1 here, you see metal 2 here, and that way this one could go this way, and I'll draw an X indicating it's going into the screen. So you can actually have them running in different directions. So you have to worry about how far these two are away from each other, what direction they're going. You have to know about the width and the thickness of the wire. And so here, this is 0.6 millimeter, 3 metal layers, whereas modern kind of use 6 to 10 metal layers. And your goal should be, you have to worry about supply voltage, ground, and your clock signals. And then you really want your high density cells where you have a lot of work going to communicate back and forth with these different levels. So metal 1, within cell routing, you'll typically see with metal 1s. And then metal 2, so let's say you have a cell here, and let's say you have a say you're making an adder and you have a number of cells here. And so you'd use a metal 1 to connect these two. And then you know how you have a second adder here, we have a carry out. That's typically where metal 2 is coming in. So for some reason, metal 3 is going this way, metal 2 is going to go this way because that's your carry in, and all your, and then those would go to your multiplexers, which again, you have metal 1 inside.
Is this literally different types of metal? Or?
Yes, literally. And what you'll discover, and let me get down to this. Yeah, so here's this diagram I wanted to show you. So let me zoom in on this a little bit. All right, so these are actually different metals. So this is a stack of 90 nanometers versus 45 nanometer technology. So here, it actually has eight different types of metal, right? And the transistors are down here. You can let me see if I can zoom in a little more. There we go. Okay, so here you got the actual transistor design. Can you see this right here? You actually have your wells, and they're connecting to the gate. And then you're actually having communication going on here. So you have all these different wires going in between. So you see this is the 90 nanometer here on the left, and this is 45 on the right. So you see how the metal 1 is in the actual technology is much smaller? And you're using 8 different metals to try to communicate. You're trying to create dielectric space between each one of these. So the whole goal here is to try to prevent these from having too much of a capacitive effect. So you want the transistors to actually work. And so what ends up happening is in this diagram here, see how the thickness and width and the space that you need for each different metal. For metal 1, see how they're significant. The thickness is in nanometers, so it's 144 nanometers, and you're getting up to 7 micrometers. So it's actually significantly increasing. All of these are increasing. And the reason why is, going back up to this little diagram up here, so you have these thin, narrow, high density cells. And so density versus speed, so this is where your good design requires good compromise comes into play. And then your top layers are your VDD, ground, and clock. So And so for that one, that was metal 7, right? So your top layers are going to be these guys here. And if you recall what I mentioned earlier about the thicker wires having the least resistance, you want that supply voltage to have as little resistance as possible because you want it to get there, and then everything else you deal with, how you design your transistor cells and how they communicate. And so if you actually look at your lithography video again, you can see that you keep doing all these layers. You etch them in different sizes with different metals. That's what's actually going on there. So you see there's one other thing I want to show you. So because remember, these are coming from VDD. These inputs are coming in from VDD here and here. So you see they're coming all the way down here, and they're being connected with your contacts. That's where contacts come into play, if you recall those. All right, so in order to do that, we're going to do some RC networks designs. And so wires can be considered a distributed system. And so there are 3 different types of models here: the L model, the pi model, and the T model. And so our model, let me see the L model, it looks like an L. The pi model looks like pi. And the T model looks like T. So the R model kind of just uses the resistance and the capacitance, kind of what we've seen before, right? So the pi model cuts the capacitance in half and uses that resistor. And then the T model cuts the resistance in half and uses the full capacitance. So ultimately, you want to be trying to cut the wire down into a certain number of segments. So it's like a series. And ultimately, you want it to be, you don't want it to have, you don't want it to be like a calculus problem. So these a 3-segment, so this is n segments here. This is talking about 3 segments. 3-segment P model is accurate to 3% within simulation. So it's 97% accurate in simulation. So the L model needs 100 segments for the same accuracy. So obviously you want P model, that should be pi. So you can either have 100 of these or 3 of these. What do you think would be easier to write the code for? Yep. Okay, so here next thing we need to do is we need to relate our P model and our T model to RC over 2 no matter how many segments. Therefore, we need to relate it to resistance and capacitance. So let's see how we go and do that. Okay, so now we take all these values that we were able to get before. So we had our thickness. We have our resistivity of the wire. And then we have our length of the wire, the width of the wire, and the thickness of the wire. So, because that's a kind of a R equals, and then you have, remember that, and the length of the wire, T, thickness of the wire, and the width of the wire. And so specifically, this segment of it, so let's define the resistance of a uniform slab of conducting material can be expressed as, just with this equation, where mu is the resistivity of the uniform slab of conducting material. And so if you have little thick slices of it, that's where 4.23 comes in. The sheet resistance is a measure of the resistance of thin films that are nominally uniform in thickness. And so that's just sheet resistance, R dot, is equal to that. And you can tell the units work out because length and width are going to cancel. All right, so I'm going to scroll past 4.22. And so here we have this example question. So we have a wire, a certain amount of length. Both of these wires have the same thickness, but as you can tell, the length is twice as long, and the width is twice as thick. Here, determine which wire has the greater resistance. So we had our equation. Resistivity, they have the same resistivity, right? They have the same thickness, length, and width. And so R2 is going to have 2L and 2W. And those two are going to cancel out, right? So it turns out these have the same resistance. If you recall, the longer wires, their resistance tends to go down. And doubling your thickness, then you make sure that these actually come out the same. So this is not a type of question I'd ask on an exam because I think it's very silly, but I've included it because I kind of want you to get the idea of how this equation works. Does anybody have any questions on that? All right, so I'm going to scroll past the diagram. And so what we're going to talk about is after 180 nanometers, so we're now dealing with Moore's law consequences here. So before that, we had this, basically they were all aluminum. And you're going to see aluminum, the bulk resistivity, it's microohms per centimeter. And so thickness is, in distance, so they end up canceling out. So that's how we get resistance. So the resistance becomes 2.8. However, they typically use copper. So we need a diffusion, however, we need a diffusion barrier because they tend to diffuse into silicon and damage FinFETs. Because we don't want these actually going into the transistor itself. We want them to stay outside, bring our electrons or holes to us, and then we take care of it. So this table is going to, this will be, any value of this on a question is going to be given, as you'll see. But the whole idea is that titanium has a very high resistivity, and silver has a low resistivity. However, as you can probably imagine, the trade-off in... So let me ask you guys, instead of just saying it. If silver has a lower resistivity than copper, why aren't we using silver? Yes, it's super expensive. So, we got aluminum. Next best one's gold. Nope, not gonna be able to do it. Silver? Nope. Well, copper's really cheap. Let's do that. So, what's the problem with copper? Well, when it actually gets into silicon, it tends to diffuse into it, and the result is that it actually kind of damages the transistor. Well, crap. How do we deal with that? Well, we just put a diffusion barrier. It creates a little more internal capacitance, but it makes up for it because we've cut down on the bulk resistivity by a substantial amount. All right, so here we actually have a more appropriate sheet resistance type problem. So we have a 0.17 micron thick copper wire in a 65 nanometer process, and the resistivity is 1.7. And remember, it's in ohms over centimeters. Find the total resistance if the wire is 0.125 micron wide and 1 millimeter long. So here's how this all comes out to play. Resistivity is 1.7, which is 1.7 times 10 to the negative 8 ohms per meter. So remember, this is given in centimeters, right? So I just converted it to meters. So it was 1.6 micro ohms per centimeter, right? So that's actually 1.6 times 10 to the negative 6 ohms over centimeter, and this is in micrometers. So in order to get it in, so basically I just, times 10 to the negative 3 centimeters per meter, it goes to 10 to the negative 8. Wait. Oh, centimeters is 10 to the negative 2. Sorry, that's 100. 10 to the negative 8. And then 0.17 times 10 to the negative 6 meters is just this value here, the thickness of the copper. So now the meters go away. So we have 0.125 micrometers and 1 millimeter. So 1 millimeter is actually 1,000 micrometers. 0.125, and then we plug that into a calculator and we get 800 ohms. So on this type of question, for sheet resistance, the key thing is you got to make sure you keep track of your units. And I might have done you a disservice by doing it like this. Actually, no, probably didn't, because you're going to go, okay, well, why is this is 1.7, well, why is that 10 to the negative 8 in your studies? I hope you know that centimeters is, right? If you've graduated 4th grade. Okay, centimeters, oh no. Why can't they just put it in gallons? Okay, so does this make sense? What I did here? So here we've been talking about this parallel plate capacitance where we have this thickness of the oxide. And we have the permittivity. And then we have the dielectric, times the width and the length here. So here we start dealing with increasing the distance between the wires. And so if we make the width and the thickness, if we make these bigger, we're increasing the capacitance. But if we have it here versus if we have the wire here, then ultimately the capacitance is smaller, because the further it is away, the less ability it has to actually hold the charge. So we use this equation here. So we have the permittivity, the oxide is equal to KEO of the free space. So if we recall, these numbers are 8.85 times 10 to the negative 14, and the permittivity is 3 times the permittivity of 3 space, and you have to multiply that by 3.9 for, silicon dioxide. So now you're going to see this term a lot, especially when you start talking in cadence about low K. So what's actually going on there is, let's see if I can Okay, so the Arizona State University has these predictive technology models. And so we're going to be, a little later in this course, we're actually going to go into what these mean, but this is like low power and this is high performance. So what do you think this high K means? Yeah, it's actually, see here we have our 3.9 there. So what's going to happen is if it's trying to have, typically in modern technologies want it lower than 3, but here they've put it into 3.9. So if we here, we got 3.9. See how these are kind of, we haven't learned, of course, you haven't learned about all of these different meanings and why they have it there, but you're starting to recognize some numbers. TOX, TOXP, PMOS versus NMOS. So you're starting to, so this is a model NMOS. The supply voltage is 0.95 volts. And so all of these apply to different quantum mechanical principles. What do you think that is? Threshold voltage. Very good, very good. So, and we're going to be starting to learn about some of these, but here we got a lot of capacitances, right? What is CGS? What do you think that is? Gate source, gate drain, gate body. But yeah, so all of these are different. So this is actually, they have models from HP, high performance NMOS. Where's K? Bulk. So in their models, they all use 3.9. They're still using silicon. So basically, if you're trying to have low K dielectrics, which in this case, you're trying to reduce the capacitance, the internal capacitances, then you're dealing with, they're just saying they're just using air pockets. So here, this is a complicated equation where they just kind of throw these numbers here. They're relating to width and the height. I'm not going to expect you to memorize that. That's just determined through experiment. But then we start having multiple layer cross sections. And so this is where everything starts tying into play. So you have this space here between these two wires. You have a space between these two wires. You have a space between these two wires. You got the space here, right? So you have the width of the transistor, the width of the wire. You have the length of these wires. So these are going, let's say these are going in, and this layer is going that way, right? So here we have the thickness here, and then here's your dielectric height. So the dielectric is what's between the wires. And so tying it back into these equations, we have to worry about how far these are away from each other. And then what we're going to see a little bit is what's the actual value of the wire, because then you're creating potential. So what ends up happening is we derive this equation where we have the permittivity of free space times the length of the wire, and then we just the dielectric constants between the wires are here, and then this fringe capacitance, I probably skipped over that, yeah, better fit for, basically it's relating our distance and our width of the transistor together. So what's going to happen here is now we're going to start talking about how we use wires to determine how we drive cells. So here we have an inverter that we've done all. Remember, we did all our equations from section 3 about how do we size transistors and how we do Elmore delay. So we've determined that we have a 10x unit inverter driving a 2x unit inverter at the end of this 1 millimeter wire from example 4.8, right? So we now have, let's suppose that the wire capacitance is 2 femtofarads per micrometer, and that unit size NMOS transistors have a resistance of 10 kilo ohms and a capacitance of 0.1 femtofarads. So now we're going to estimate the propagation delay using the Elmore delay model, and we're going to neglect diffusion capacitance for the time being. So here's what's happening. So we have a 10 size unit capacitor, unit inverter, sorry. So we put in our resistance here for the sheet, and then we're increasing our width by 10, right? So we have a 10x unit inverter. And then we have a resistance of 10 kilo ohms. So what's going to happen is we used this equation before to get 10 kilo ohms. And then we're just dividing in both sides by 10 because of 10x, because that's the width from down here. So that actually becomes the driver inverter just has a resistance of 1 ohm. And from 4.8, this value is from 4.8, remember, was 1 millimeter length wire. So that became 100 micrometers, 1,000 micrometers. And I put it in there because our capacitance of our wire is 0.2 femtofarads per micrometer. So this actually is 0.2 femtofarads per micrometer times 1 millimeter times 1,000 micrometers per millimeter. Micrometers cancel out, and then we have the wire capacitance becomes 200 femtofarads. So here, let's tie this in the next part. So our unit transistor has a 0.1 femtofarad capacitance, right? So now we're multiplying it by 2, and that's for NMOS. So this is actually going to become, that's actually going to be times 2, which is going to equal 0.2 femtofarads for the NMOS. And also, we have to worry about width and length ratio, because remember the PMOS is four to 2, right? So we multiply that by 2. Or, I'm sorry, the ratio is 2 to 1, so we multiply it by 4 by 2. So that becomes 0.1 times 2 plus 0.1 times 4, which then becomes 0.6 femtofarads on the output. So here's how all these numbers tie together. So we have the capacitance of the wire, we have the resistance of the 10 times unit inverter, and then we're going to have the resistance of the 2 times unit inverter. We're going to put that all in there. So remember, we got 200 femtofarads. If you recall from the, let me scroll up to the 4.8 for a split second. If you recall, we calculated that it was 800 ohms, right? never mind. I thought up and I already included it. So we have 800 ohms. We have 1 kilo ohm for the input. We have the capacitance of the wire is 200 femtofarads. And then we have 0.6 femtofarads on the output. So here's what we're going to do. We're going to use a P model. And we're going to have an input resistance of 100,000 ohms, 1 kilo ohm, right? And then we figured out that the wire capacitance is 200 femtofarads, right? So if we use the P model, that means we're splitting the capacitance in half. And we're split the capacitance on each side of our calculated wire resistance. So what's going to happen is we're going to have a capacitor here that's going to be 100 femtofarads, right? And then we're going to have an 800 ohm resistor. And then we're going to have another 100 femtofarads. So this is another 100 here. And then on the output, we're going to put 0.6 femtofarads. And this, of course, goes to a ground. So that's how we derive that. And that is how we derive this circuit. So to review, the first thing we did is we calculated the input resistor. It was a 10x unit inverter. So therefore, we were able to figure out that, just to review, we said that was 10 kilo ohms. We divided it by 10 because based on our sheet resistance, we were able to divide it by 10 because of the width. We found the capacitance of the wire. We divided it in half because of our pi model. So this is the wire. And then we're driving a load capacitance. So we know that it's 1 for a unit inverter. The input for the NMOS is 0.1 femtofarads. We multiply that by 2 because it's a 2 times unit inverter on the output. So that drives the NMOS. Recall that the PMOS is 2 to 1. In that case, it's 4 to 2. So you have to multiply 0.1 by 4. That gives us 0.6 total femtofarads. And so all of this is going to tie into your propagation delay. Remember this equation here? Remember it's R1, C1, R2, R1 plus R2, C2. Remember all those? So remember, the other thing to remember in this as we start doing this is that capacitors in parallel add like they're in series, right? So this becomes 100.6 femtofarads. So here this is 1,000 ohms times 100 femtofarads for this part here. And then for R1 plus R2, it becomes 1,800. We've combined these two capacitances as C2 in this case. So that becomes 100 plus 0.6 femtofarads. And you take that out, and then the propagation delay becomes 281 picoseconds. Does anybody have any questions about that? I know I just threw a ton of concepts at you right there. Pretty square. So if I were to change this problem and say, instead of a 10x inverter, I made these both NAND gates. There's only one difference you'd have to worry about, right? Because in the case of the inverter, you're driving both the PMOS and the NMOS, right? So if you recall, you had a table from before that related, we actually derived all the relationships between the input capacitances of an inverter versus a 2-input NAND gate versus a 3-input NOR gate, right? And it's just 2n plus 1, based on the number of inputs. We derive that. So basically, all you would do is in this step, change it. Instead of 4/2, you just figure out how the inputs relate based on the number of inputs. You plug that in, and other than that, it's the same thing. Because you have one output driving, each input on the NAND gate is going to drive a one PMOS and one NMOS transistor, right? So it's fundamentally the same. Okay. Forgive me, I usually get many more questions about this, so sometimes I get nervous when students don't ask questions. It's either they all know and I explained it well, I'm a genius, or it's 9:53 a.m. and people are wiping the crust out of their eyes. You have multiple students doing that, so you just hope that students eventually get it, So, I do hope I created an environment where students feel like they can ask questions. Anyway. Okay, so I went over the energy equation, and just to see if anybody's paying attention before someone else besides George. If I wanted to turn this into power, what do I have to multiply this side by to do it? Frequency. All right, so everyone's a little more awake. Okay, so if we have this example from 4.9, and we had the wire capacitance is 0.2 femtofarads per micrometer, and the voltage is 0.1 volts, then it just becomes this, right? CLVD squared, since it's 1.0 volts, it comes out to be 1. So how this ties into finding the power consumed by the metal, we now have a full microprocessor, 20 millimeters by 20 millimeter. So you're actually going to, in your lab reports, you're actually going to have a die area inside a pad frame, and you're going to have this design, right? And it's going to be running at 3 gigahertz in the 65 nanometer process. So here we have a layer of metal that's routed on a 250 nanometer pitch, and half of the available wire tracks are used. So we have all these wire tracks. So you can imagine the first thing we're going to do is try to calculate the number of metal tracks before we do anything else. And then we go, okay, well, we're using half of them. So also the wires have an average activity factor of 0.1. So that means every 10 clock cycles on average, we're going to be switching from a 1 to a 0. I'm sorry, we're going to be switching from a 0 to a 1 in the wire. So just like the previous problems, we're going to suppose that the wire capacitance is 0.2 femtofarads per micrometer, and we're going to determine the power consumed by this whole layer of metal that we have in here. So the first thing we have is we're going to calculate our length. So it's 20 nanometers, right? And so one of the tracks is going to run this way, and we know that this is also 20 nanometers, and that each one of these is going to be 250 nanometers. So we got to figure out how many of those exist before we can do anything else. So in this case, it's just 20 times 10 to the negative 6 over 10 to the negative 3 over 250 times 10 to the negative 6, which then comes out to 80,000. In that case, we know that half of them are being used, so we just cut it down to 40,000. And then we're going to figure out the length of the wire capacitance. So since we've assumed that the wire is 20 nanometers because it runs the entire length of the area, we know that our capacitance per unit length is 0.2 femtofarads per micrometer, and we know it's 20 millimeters. And we're multiplying it by 40,000 because there are 40,000 of them. Because we're trying to determine the power consumed by the layer of the metal. So that means we want all of them involved, right? Does that make sense? Okay. In fact, I probably could have put C total to make it more clear. So you multiply this all out and it becomes a 160 nanofarads. And then, since we know our capacitance, we know our supply voltage, we know our frequency, and we know our switching factor, we now can calculate the total power consumption of the circuit. So here, we just plug in 0.1. We have our overall capacitance, which is 60 nanofarads. Supply voltage is 1 volt. And the frequency is 3 gigahertz. And in this particular case, it comes out to 48 watts, which is actually very, very high. That's not something you typically want. And I've made a note underneath that in this case, we have talked about one layer of metal. And we have one layer of metal where we have wires going completely through all locations, right? So this is this problem has presented a worst case scenario. So what ends up happening is you want a number of metals communicating in different directions so you don't use all the slices. And what that ends up doing is reducing your switching factors. When you reduce your switching factor, this significantly pulls down your power consumption. And by having different metals and you don't want to use up the whole sheet, that significantly reduces your capacitance. So that ultimately would bring down your number of tracks. Does that make sense? Okay, we can talk about crosstalk, and then that'll be a good place to end lecture. So I've been alluding to this concept all lecture today. So we have this idea where we have two wires going like this, right? So both of them are a 1. Well, what ends up happening when one of them changes to a 0? Well, we have a voltage potential here, right? And so if I'm a hole here, actually if I'm an electron, I'm in a 0, and suddenly I notice that I have a 1 over here. Am I going to be more likely to want to go to this destination that might be way over here, or am I just going to want to zoom over there? So that's this concept of crosstalk. So we have to worry about that in our designs, right? So we have noise on non-switching wires because, as we just saw, we're messing with the wires that are switching because it's impacting that result. And then the switching wire, it has that increased delay because instead of wanting to go over here, they tend to want to be held up a little bit because of the capacitance and because of the difference in voltage potential. So what's going to happen is we're going to model it with these adjacent capacitances, and we're going to worry about the top and the bottom transistors running next to them. If you recall that model that I drew up a little bit ago. So here's that model. We have two wires. We have adjacent capacitances, and both of them have a ground capacitance with your dielectric, right? And so the way we figure this out is we relate everything to this concept of the Miller coupling factor. So this table here, so the topical guide objective is both the definition and the table. This relates our capacitances to how it's switching with another wire, right? So we have wire A and wire B. If you see this diagram up here, we have wire A and wire B. So if wire B is constant, then the change in voltage is just going to be VDD, right? And the effective capacitance is going to be the ground capacitance plus the adjacent capacitance, right? Because that's what's naturally there. And so the Miller coupling factor is 1, and they're just both the same, right? So the second entry in the table is what happens if A and B switch at the same time to 0. So now our change in voltage is 0 because it hasn't happened at all yet, right? And then 0 and 0, our effective capacitance is equivalent to the ground, which means our Miller coupling factor becomes 0. So then our worst case scenario is, let's say they are both zeros and it switches opposite. So 1, 0, and then we have a case where it becomes 0, 1, right? So this is our worst case scenario here. So now the change in voltage is we're going to be 2 times the supply voltage. And then the effective capacitance is be ground plus 2 times the adjacent capacitance, because we have both of them switching. And therefore, the Miller coupling factor is going to be 2. And so this is the TGO, and let me read the formal definition. The Miller coupling factor describes how the capacitance to adjacent wires is multiplied to find the effective capacitance. So you have 2 wires switching. Either they just stay the same and you have some sort of effective capacitance, or it switches with A. So let's say we have a situation where A is 1 and B is 0, right? So the difference in voltage is the supply voltage. So they're just constant. So then here, what ends up happening is that we have some where it's 1, 0, and then it switches to 1, 1. So therefore, our difference in voltage is 0. And therefore, the adjacent capacitance is now negligible, and now we just deal with the capacitance to ground. And then our third case scenario, if it's 1, 0, and at the same time they switch opposite. So now it's 0, 1. So now because of the switching, we have 2 times the supply voltage. And then we have to deal with 2 times the adjacent capacitance. So you can see that the Miller coupling factor ties in with this adjacent capacitance. So if it's just adjacent's 1, switches with it, becomes 0, it becomes 2 times. As you see, it also ties into how it's switching with the supply voltage. So I made a little note there. Some designers use a Miller coupling factor of 1.5 as a statistical compromise in estimating propagation delay. So if you're thinking about millions of different switches and how everything works out, over time it's going to average out to 1.5. Because you're going to have the scenarios between switching at the same time as opposed to switching opposite. It comes out to 1.5. So let's work on this problem here, 4.11. So now this is a good combining concepts type problem. So wire combination and propagation delay. So what's going on here is we have each wire is 1 millimeter lines. There's a capacitance of 0.08 femtofarads per micrometer to ground and 0.12 farads per micrometer to its neighbor. So you can see which one's the adjacent and which one is the ground capacitance. Each line is driven by an inverter with a 1 kilo ohm effective resistance. Estimate the contamination and propagation delays of the path. Neglect parasitic capacitance of the inverter and the resistance of the wires. So the first thing we're going to do is we know that the wire is 1 millimeter, so we're going to take our ground capacitance and our adjacent capacitance and calculate those. We do so with 0.08 femtofarads per micrometer divided by 1 millimeter, and 1 millimeter is 1,000 micrometers. So you multiply that out, it becomes 80 femtofarads. Same thing here, this becomes 1,000 micrometers. So 0.12 becomes 120 femtofarads for the adjacent capacitance. And so here's how we're combining concepts. The contamination delay is what happens when they switch in the same direction, right? So the Miller coupling factor is going to be 0 in this case. So it's just going to become RC. So we have 80 femtofarads, because that's ground capacitance. I just switched this up. It's 1 kilo ohm, which we get from the effective resistance from the statement, right? So these are what happens when they're in the same direction. So if in their opposite direction, that's what happens when you get propagation delay. So propagation is going to be the maximum possible delay in this case. Does everybody see how these concepts of contamination delay and propagation delay tie in? So contamination is what you can't change. It's just there. So if they're switching in the same direction, there's not much you can do about it. For the propagation delays, how is the design of your circuit and the signals actually fighting against each other? In this case, we're actually here. We have C, goes to capacitance to the ground, times 2 times the adjacent capacitance. And then again, we have 80 femtofarads times 2 times 120, which we get from here, times 1 kilo ohm, which is the effective resistance, and that gives us 320 picoseconds. Let me see if that's the end of section 4.
That's the lowest delay between two wires, and the maximum.
Yeah. So the question is, this is the lowest delay. So in this case, right. So if we tie this back into our table, remember we had the Miller coupling factor of 1 is when it's constant. So there's no switching at all, right? I'm sorry. This is. So then we have a switching where it's in the same direction. So if it was in the same direction, it would be R times C ground plus C adjacent, right? Which would be 80 plus 120, so that would become 200 femtofarads times 1 kilo ohm, which would be 200 picoseconds, right? So then that's just the normal switching delay, but then the propagation delay here is what happens in the worst case when they switch in the opposite direction. So in this case, not opposite direction. In this case, one of them was 1 and the other is 0, and then it's 0 and 1, right? So that's our worst case scenario here, tying into the Miller coupling factor. Did that answer your question? Okay. Does anybody have any other questions? All right, so what I'd like you to do over break, this assignment, and then to complete the labs, you'll be, if you get through section 6 on remember the Verilog, teach yourself. If you can get through section 6, so do the same thing, that Verilog assignment will count as 3 homeworks. So do the same thing. Make sure I can read that you've gone through it. Keep those notes because especially in lab 3, you'll be doing minor modifications to Verilog code. You'll have a Verilog MIPS data path that you will just have to make minor changes to the control signals. And it tells you it's not as complicated as my 385. This should be, you go through, you follow it. Sometimes it gives you, it's going to be a little complicated if it doesn't want to cooperate, but by and large, it should be it's a very straightforward lab. But ultimately, if you get through section 6, you should be able to sufficiently complete everything. So, and have the final drafts. I've told everybody by Friday, right? Okay, good. Good deal. All right. Well, in that case, y'all have a good break. Or I didn't put break in quotes on my syllabus, so. Scam.